Okay, welcome everyone. This is the first lecture of Power Management IC, which I am offering on NPTEL. Uh, so, uh, here is the course outline. So, I have divided this in this course in 4 portions. So, first we will go through introduction to power management and voltage regulators. So, we look into why do we need power management, what are the different applications, what are the different types of power management, and how the power is delivered in a VLSI system, and what are the different performance parameters associated with voltage regulators, just such as line load regulation and line and load transient, settling time, and then local versus remote feedback based on accuracy requirement, how we choose whether we have to need a local or remote feedback. Kelvin sensing, which is mainly used for again accuracy reasons, and point of load regulators. So, and in the second part we will move to linear regulators. We will talk about band gap voltage reference, low dropout regulators, which is basically a linear regulator, source and sink regulator, shunt regulator, pass transistors, error amplifier, small signal model and stability analysis, how we compensate a regulator. There are different types of compensation which are used in linear regulator. Current limiting and PSRR or power supply rejection ratio, and we will also look into what are the difference between NMOS versus PMOS in terms of performance and area, and then we will look at a current regulator. Third part we will talk about switching DC to DC converters, what are the different types like buck boost, then power FETs, how we choose L and C, which is inductor and capacitor, which is mostly external, then PWM modulation, leading, trailing and dual edge. These are different types of modulation techniques used in DC to DC converter. What are the different losses which are incurred in a switching regulator, output ripple, then different types of control like voltage current mode control, then CCM and DCM modes, which is continuous conduction mode and discontinuous conduction mode, and then other types of control techniques such as stereotic control, which is nonlinear control, and switch capacitor DC to DC converter, which does not require an inductor. We will talk about that as well. Then we will do a small signal model of DC-DC converter, loop gain analysis, and how we compensate a switching regulator or DC to DC converter. We will look at different types of compensation techniques, which is type 1, type 2 and type 3 compensation, and how we compensate a voltage mode DC to DC converter. And we will also look into how we compensate a current mode DC to DC converter, and how we select a topology for a given specification, how we select the switching frequency. So, basically we will look into how we exactly design, or what are the steps used in the design to when we are given a spec for or a specification for a switching regulator. And we will also talk about some building blocks which are used in switching regulators, like your gate driver, PWM modulator, error amplifier, oscillator, ramp generator and feedback resistors. We will also look into some different current sensing techniques which are used for current mode regulator as well as current limit for protection purpose. Then pulse frequency modulation and pulse skip modulation, which is PFM and PSM mode for light load. Then what are the effect of parasitics on reliability and performance, current limit and short circuit protection, soft start control. Then we will also look into chip level layout and placement guidelines, and then board level layout and guidelines for EMI consideration. At the end, in the last part, we will look into, this will like I will briefly talk about some advanced topics in power management, such as digitally controlled DC to DC converters, digitally controlled LDOs. This digitally controlled LDOs may be covered in the linear regulators already, so we may skip in this part. Time based control for voltage regulators, then adaptive compensation, dynamic voltage scaling, single inductor multiple output converters, and DC to DC converter for LED lightings and displays, and lithium ion battery charger. So, this course is equivalent to Power Management IC, which is taught in, which I am teaching in IIT Madras. And if you want to look at the course page, I already have a course page for that. So, you can go and look at it. I have some previous years video recording as well as handouts for this course. So, if you go to this department, this is ICS or Integrated Circuits and System group page. If you go here, go to teaching, and you will find E5325 Power Management IC course, and here you will see recorded lectures. So, for this year I have only handouts, but if you want to look at a previous year's lecture, I have videos there. So, more or less you will find same content, and if you look at the table of contents here, it is exactly the same what I just showed you on that slide. Okay, so what is power management? Power management deals with the efficient and reliable power delivery to a system. So, it could be your voltage conversion from one power domain to other, which means you have a DC input and you want to have a different DC output voltage. So, it is called DC to DC conversion. Let us say you have a 5 volt and your system requires 1.2 volt. So, you have to basically down convert from 5 volt to 1.2 volt. So, that is called DC to DC conversion. It could be AC to DC or DC to AC conversion, which we call rectifiers and inverters. So, let us say you have AC input, which could be your coming from your AC line, 220 volt RMS at 50 hertz. So, you require a rectifier, just which is shown on the right hand side, this one. So, this gets converted to a DC, and then all the ripples are filtered at with this capacitor, and you get a DC voltage. So, that is nothing but AC to DC conversion or rectifier. Then DC to AC conversion, like I have a DC source, let us say battery, and you want to convert to AC. The example is your inverter, which we use in our homes. So, that is nothing but a DC to AC converter, which we call inverters. So, that is also a kind of power management, and it may also be associated with voltage current measurement. Which is basically what we do here, we sense the voltage and current. One example could be your in the solar basically converters, or I mean when you harvest the energy from solar panel. So, it mostly requires something called MPPT, which is maximum power point tracking. So, you need to measure the power. So, in order to calculate the power, you have to sense the voltage as well as current, because power is nothing but product of voltage and current. So, we need to measure voltage and current in order to operate at maximum power point. So, solar and the MPPT controller is basically drives nothing but your DC to DC converter, and based on the MPPT point, it decides at what load current to be supplied, or if you are charging a battery, then at what current that battery should be charged. So, and it could also be associated with managing losses or heat. So, let us say your load is drawing few amps of current, and after some time it gets heated due to losses, I square R losses in that load. So, and most of the system have a maximum temperature specification. We cannot operate beyond that, because there is a risk of damaging that system. So, and best example could be your cell phone actually. I mean, if your cell phone gets heated, or let us say you are charging a battery, it gets heated, the battery may explode, or your cell phone may break. And if you are your phone has a metallic cover, then it may get heated, and you do not want your cell phone to heat like 60 degree, 80 degrees. It won't be, you cannot even hold your phone at that high temperature, and there is a risk for damaging your parts also which are inside your cell phone. So, what we do actually, when temperature goes beyond certain range, let us say minimum temperature, let us say you have specified at 110 degrees. So, when it goes 110 degrees, so if 100% is a, let's say 10 amp current is 100%. So, then you derate the current by 10% at every 10 degree Celsius increase. So, by the time it reaches 160 degree, you will be at 60% of the total current. So, which means instead of 10 amp, you will be supplying only 6 amp, or if you are charging your battery, let us say with a 1 amp current, then you will only be charging with 600 milliamp, because you do not want your battery to heat up. So, that is also a kind of power management which is used in most of the systems, especially the integrated systems like cell phones. Then another one is your dynamic voltage scaling, which depending upon the performance required by the system, it changes the voltage dynamically. So, example is your CPU. So, when the CPU is running at a full performance, so let us say you are running lot of applications on your cell phone, let us say you are watching videos, listening to music, or same time you are surfing the net. Okay. So, lot of processing is going on in your processor, and it requires that time lot of power. So, you increase the voltage, because and most of you would have heard of processor overclocking. So, what you do, you operate the processor at higher frequency. When you operate the processor at higher frequency, that means it has a more power consumption. So, you increase the voltage also, so that you can run your processor at higher frequency. And when performance requirement is very low, so let us say you are not watching any video or anything, or let us say your phone is in the silent mode, and you are not surfing the net, or lot of processing is not going on, then you can reduce the voltage, and same time the frequency is also reduced for the processor. So, that is called dynamic voltage scaling, and sometimes it is also called dynamic voltage frequency scaling, where we scale both frequency and voltage. That is why it is called DVFS, dynamic voltage frequency scaling. In some cases, we only change the voltage. We will talk about that when we talk about advanced power management techniques, but in the processor most of the time we change both frequency and voltage. So, DVFS is used there. So, that is also a kind of power management technique which is used in integrated systems like cell phones and your PCs and tablets. So, this efficient power management, we can say it is achieved by controlling or managing power delivered to the load. So, what you do, depending upon the performance required, you basically change the power requirement or current, or like in the solar application, you want to operate at maximum power point. So, you measure both voltage and current and calculate the power, maximum power. So, a lot of different control techniques are used in order to achieve this efficient power management. So, there are mainly two types of power management. One is high power, other is low or mid power. When we talk about high power, we talk about hundreds of watt to kilowatts range, and most of these systems are directly powered by AC. So, and since at such a high power, it is very difficult to integrate everything on chip. So, they mostly use a discrete semiconductor devices, which are your power MOSFETs, BJTs or diodes, and very large passive components you can see here. This is your electrolytic capacitor, this is your inductor, then these are like all these cylindrical these parts or devices are nothing but your capacitor. So, you can see lot of passive components here compared to your controller chip or your power FETs, which is a semiconductor. So, these are like your semiconductors, this one and this one. Rest of the thing here are like your passive components. So, looks like 90% components are here passive, even if you are using these semiconductors, they are mostly discrete actually, except the controller. Your BJTs, diodes or MOSFETs, everything is discrete. They are not integrated on the same chip where the controller is. On the right hand side, your low or mid power, when we talk about its range is milliwatt to tens of watts, and powered from battery. The example is your cell phone, because it is powered by a single lithium ion battery, and these batteries have a capacity of 3000 milliampere to 5000 milliampere hour. Yes. Question? Okay. Okay, so powered from lithium ion battery, and so in this case what we have integrated controller and power FETs with few small external passive components. So you can see here, this is your power management chip, which is your integrates your controller as well as power FETs, and outside you see inductor and capacitor. You may have some resistors also for sensing purpose, but mostly use one inductor and one capacitor, or maybe two capacitors for filtering both input and output supplies. So, but the point here is like the number of discrete components which used here are much less compared to which we used in high power, and that is the main difference between your power electronics and your power management. A lot of people get confused with the power electronics and power management. Sometimes they think power management is same as power electronics, but there is a huge difference between the two. The power management deals with chip level design, while power electronics deal with discrete level design, because they are dealing with very high power. So, they have a different requirement, the devices used are completely different. Okay, we are dealing with order of amps of the current, they might be dealing with the hundreds of amps of current, or if you talk about the watts, they might be dealing with kilowatts, we are dealing only with tens of watt. So, and slowly, I mean the integrated power management is moving towards high power. So, it's gaining the some market from the power electronics, and which basically you can say there is a little overlap between the two power electronics, and but if you know the power management, then you can easily go and basically design a system for power electronics requirement, integrated system. But if you don't know the power management IC, then it's or let's say you have you have taken any course on power electronics, that does not mean that you can do a power management IC actually, because it requires all the chip level expertise, which means you need to know the basics of transistor, you need to know how to design op amp, how to design your controllers and everything at a chip level actually, at transistor level, which most of the time power electronics people don't know actually. They only deal with the discrete level design. So, they don't know what is happening inside the controller or inside the chip. So, from theory point of view, you will find some overlap, because the basic concept of regulators or DC-DC converter remains same, but the difference is mainly at the implementation level, because in the power management IC we mainly deal with the chip level.